when I first met Leah, I think she was a sophomore in organic lab, and I was doing the lab instructing that year, and that was my first time here at Lawrence in the organic lab too. So I was trying to build my research program here on campus. I had just gotten a grant, and so I announced in class, hey, I have a grant and I need some students to work in my lab. And that afternoon, Leah came to my office and said, can I work in your lab? And I said, okay, sure, why not? And so that's how it all started. We did an independent study the next term, and I was always struck by how very few questions Leah asked me. I would explain some complicated concept to her, and she'd say, yeah, okay. And I'd say, okay? And she'd say, yeah. And then that was it. So she picked up on everything really, really quickly. And I think a lot of you, or all of you probably know, she's also on the basketball team at Lawrence, and brought a lot of her strengths from being a basketball player into the lab. She was a great teammate of the labs, taking people to lunch in her car all the time over the summer, and was a good lab citizen as well, and a very persistent chemist as well. You'll see one reaction, I think, has probably got to be like a drill at some point, right?
Yeah.
So she'll tell you all about that reaction and some other ones today. So without further ado, please welcome Leah. Enjoy.
As Graham said, I'm Leah, and today I'm going to be talking to you guys about my research that I've done for the last 2 years on design principles of stable organic radicals with luminescent properties, which is a really long name and probably pretty confusing, and I promise you that it's not abstract, it does relate to your lives. So the first thing is, I'm sure that we are all aware that we have phones and laptops, and one of the things that we always complain about is how our phones die so quickly. And there's obviously a lot of contributing factors to that. But one of the main ones that I am going to be focusing on is our screen technology. So at most, the technology that we're using right now for our screens is 75% efficient, which means that we're losing 25% of what we're putting into our phone through our screen technology. And so it's this inherent inefficiency that is kind of driving this project in the first place. So as I just said, our screen technology is 25% to 75% theoretical internal quantum efficiency, meaning that we are losing a lot of energy through the molecules that we're using for screen technology. And so even our newest screen technology, or our organic light emitting diodes, our OLEDs, so your new iPhone X, your LG TVs, are all still really inefficient. They are brighter and they're faster and they're easier to process, but they still are having these issues with inefficiency, and that's because of the molecular level. And so in order to understand why they're inefficient, we're going to go into luminescence. And so the first step for luminescence is absorption. So right here, what we're looking at is a Bohr model. And so a Bohr model, I have two disclaimers. The first one is that a Bohr model is not actually how electrons work, but it's just a really good representation for us to understand how they're working. And so the second disclaimer is that Bohr models refer to atoms, and I'm going to be talking about molecules. And so atoms are like what's over here on our periodic table of elements, but I'm going to be talking to them in broader terms as far as molecules, but it's just easy for us to understand at a molecular level to look at it like this. So here we have our nucleus, and then we have two red dots which are representative of our electrons. And so we have two electrons here in our ground state, which is referring to their most stable state. And what happens in absorption is a molecule is introduced to some kind of energy, and then one electron is moved up to its excited state. So in this depiction over here, we have one electron in its ground state and one electron in the excited state. And so the Bohr model is a really good understanding for us, but we can depict this in an even simpler model using lines and arrows. So on the left here, we have an energy axis, and then we have here two arrows, and these arrows are representative of electrons. And then we have these two horizontal lines, which are representative of the orbitals. And so this bottom orbital down here was the most inner circle on that Bohr model, and it is referred to in chemistry jargon as the highest occupied molecular orbital, or the HOMO. And then up here we have the bigger circle that was empty to start, and that's the lowest unoccupied molecular orbital, known as the LUMO. And so we're going to go through absorption again. So our molecule is going to interact with some energy, it's going to absorb energy, and then we're going to have an electron move up to a higher energy state. So the main point here is that absorption is going to lead us to an excited state of the molecule and also an excited state for the electron. But electrons don't stay in this excited state. They have to come back down to their ground state. And there's a couple different ways that this happens. One of the most common ways is through vibrational energy. So a molecule absorbs energy and then physically wiggles itself back down, because you have to dissipate the energy that was absorbed in the first place in order to get back down to the ground state. But the more interesting way for us, and what we're talking about in our project, is something called luminescence. So we're going to go back to our Bohr model, and so now we're going to start in our excited state. So we have one electron over here in the LUMO and one electron in the HOMO. And it's going to lose energy and get back to the ground state, and in doing so, we're going to emit photons. And that's what luminescence is. It is literally emitting packages of light that we perceive as color and light. And so we're going to go back to our energy diagram. We're starting in our excited state again. And so we have one electron in the HOMO, one electron in the LUMO. We are going to emit a photon out, and then we're going to end up in our ground state. Something that's really important to keep in mind is that the photon is emitted with a specific energy, and the energy that is emitted through that photon is associated with the energy gap between the HOMO and the LUMO. So this energy axis over here is true. So we have a difference in energy in our HOMO and our LUMO. And this arrow is literally indicating that the amount of energy that we are emitting back out is equivalent to that gap between the HOMO and the LUMO. And that's really important when we're talking about luminescence, and I'll go into that a little bit further as well. And so luminescence seems pretty straightforward. So you have a molecule that absorbs energy, and then we emit that energy back out through a photon. But it's not as simple as we might think, because electrons interact. And so as we talked about, electrons are depicted by arrows, and there's a reason for that. Because electrons can either be spin up or spin down. We can think of electrons as little magnets. And so electrons pair together and spin up or spin down. And so here, when we look at this, some of the chemists are getting a little uncomfortable, because this doesn't happen. You don't have unspin paired electrons in the same orbital. They have to be one spin up and one spin down if they're going to be in the same orbital. And this is really important when we're talking about electronic states. And so when we go into electronic states, I'm simply referring to how the electrons in a molecule are arranging themselves. And there's a couple different ways we can do that. One is the singlet state. And this is what we've been talking about this whole time. So the singlet state, we have two electrons, one is spin up and one is spin down. And so that means that in the entire molecule, all of the electrons are spin paired. Now note that I don't have the orbital line here because I'm not necessarily talking about electrons in the same orbital, but I am talking about the electrons interacting with each other in the molecule. And then we can move to the triplet state, which has three different ways to arrange the electron, that's why it's called the triplet state. The first way is just like the singlet state, it can be spin up or spin down. And then we can move to either both spin up or both spin down. And again, I'm not talking about electrons in the same orbital, I'm just talking about electrons generally within the molecule. And then finally, we have the doublet state, which only has one electron that we're going to be focusing on. And that electron can either be spin up or spin down, so there's two ways to arrange it, so it's called the doublet state. And so we're going to go back to looking at absorption. So we've seen this diagram before a bunch of times already, and now we're going to refer to this as the singlet ground state. And so the electrons here are still talking to each other. They're paired up by their spins. One is spin up and one is spin down. And so from the singlet ground state, we can absorb energy and end up in the singlet excited state, which we've already seen before. And so here we have one electron that's spin up, one electron that is spin down. They're still talking to each other. They might not be in the same orbital anymore, but they're still friends and they're getting along pretty well. But then we can also transfer into our triplet state. And here, the electrons are both spin up. So they're no longer friends, and they aren't talking to each other anymore. And so there's a couple different things that we're going to unpack here. The first one is that we have our energy axis. And so you'll see that the LUMO over here in the triplet state is lower than the LUMO in the singlet state. And that's because of entropy. So because there are three ways to arrange the electrons in the triplet state, it is a more energetically stable formation for the electrons as opposed to only having one way to arrange themselves. And so this is pretty interesting, but the question is, how do we move from the electrons talking to each other to them not talking to each other anymore? And the answer is this phenomenon called intersystem crossing. So intersystem crossing is literally the process in which electrons are no longer spin paired to one another. And they do this by non-radiatively losing energy. And so what I mean by that is that we're not using light to lose this energy, it's wiggling in some way, and so the electrons are now no longer paired together. And so I'm going to throw up this diagram. This is called the Jablonski diagram, and it's really intimidating, and I promise I'll walk you through it. So the first thing is, we're going to start down here at the singlet ground state. And from here, an electron can absorb energy and end up at the singlet excited state. And then it can fluoresce back down. So when I'm talking about luminescence, there's two different ways that we're talking about. The first one is fluorescence, which is specifically referring to luminescence from only the singlet state. So luminescence is this broad term meaning that we're emitting a photon. But fluorescence is specifically referring to luminescence from only the singlet state. But then we can move back down to the singlet ground state, we can absorb energy, and then go through intersystem crossing to unpair our electrons. And then now we're in the triplet excited state where we can phosphorus back down to the ground state. And so phosphorescence is specifically luminescence from the triplet state. And so there's a couple things we're going to talk about. The first one is that the wavelength of the photon that is emitted through fluorescence, so the wavelength from singlet state, is closer to the wavelength that we absorbed in the first place. On the other hand, the wavelength of phosphorescence, so the photon that's emitted through the process of phosphorescence, is further away from the wavelength that we absorbed. And what this is it's just a complicated way of saying that intersystem crossing is leading to inefficiency in our molecules that are emitting light. And that's happening because we cannot control this process. We can't decide, we can't manage whether or not a molecule is going to fluoresce or phosphoresce. Some molecules do both, some do one, some prefer the other, and we have no control in how that's happening. And so because of that, we know that we're losing energy through intersystem crossing, and when that's happening, we aren't getting the same amount of energy back out that we put in, which is how we're getting this inefficiency. And so the question is, if molecules are doing this and we have no control over this, how in the world are we supposed to solve this problem? And the answer is radicals, at least in theory. So we're going to start off with, again, our Bohr model. And the first thing to know is that normal molecules have paired electrons. So electrons like to be spin paired, but they generally just like to have a buddy regardless. And so electrons are only stable when they have another partner. And radicals are unique because radicals have an unpaired electron. So we just went from 8 electrons in this outer shell to now we have 7. And so we have a single electron that doesn't have a buddy, and it will do pretty much anything in its power to end up with a friend. It is desperate to get one, and so it's very reactive. And in doing so, it makes the whole molecule very unstable. And so radicals are known for being unstable species. And we know this in our everyday lives. So we have things called free radicals or reactive oxygen species in our bodies that are being made all the time. And they can damage us. And that's because they go through things called chain reactions. And free radicals are made through metabolism. So when we're changing our food into energy, we're constantly making these free radicals in our body. And what can happen is once it's made, it's going to steal an electron from another molecule, which then now this is a radical which is going to steal an electron from that molecule. And so we get this chain reaction of radicals being made in our body, which can damage our protein or our DNA, and obviously we don't want that to happen. And that's what happens when you have sunburn or aging, and I'm sunburned because we had class outside last week, well this week for biochem too, so my legs are all sunburned, and so yeah, I have a lot of free radicals in my body. But when we hear about antioxidants, that's what we're talking about, is to prevent this free radical damage. So antioxidants are important because they freely donate a radical, they donate an electron to the radical in hopes of stopping this chain reaction, which is why it's really important that you have a good diet, because then you're going to get the right antioxidants for your body. So now we know, okay, so radicals are unstable, but why do we think that they relate to luminescence at all? And so the answer is in the doublet state that we talked about earlier. So in the doublet state here we have our single electron in the HOMO, and when it absorbs energy, it moves back up into our LUMO and then can emit back out a photon. So this looks like just pretty much everything we just looked at. But the difference is that we cannot transition into the triplet state because it's not spin paired to start with, which means that there isn't any intersystem crossing involved in this process at all. And because of that, we don't have to worry about losing energy by going into the triplet state or controlling whether we're phosphorescing or fluorescing. And so in theory, doublet state luminescence, so radical luminescence, is going to have a more efficient emission than a normal molecule, which is great. So, okay, now we understand. We want to use radicals for their unique luminescent properties, but we just talked about how unstable they are and how they can harm our bodies. So what do we do with this? Luckily, there's been research done, and there are some known stable radicals. So this one on the left here is called PTM, and it's just a benchtop stable radical, which means that you can put it in a bottle and leave it on a bench, and it'll stay a radical for a longer period of time than what we're used to. And this one here is PYBTM, which is another known stable radical, but this one is luminescent. And so when we're looking at these two molecules, the first thing to note is that this dot here and here is denoting the radical. So that's what we mean when we say the unpaired electron. So in this case, the unpaired electron is going to be spending most of its time on this central carbon. Another thing to know about these molecules is that they are 2D representations of 3D things. And I have a model later on to show you what that looks like, but just keep that in mind as we're looking at what these look like. And obviously, as you're looking at these, you can see that there's a lot of similarities between these two molecules. And it was these similarities that I was looking at when I was designing my target compound, which looks like this. And so the three main things that I was looking at when I designed this molecule were aromaticity, steric hindrance, and then the presence of heteroatoms. And I'm going to walk us through each of these, and we're going to have a better understanding of why these are important to making this compound stable and luminescent. So the first thing is aromaticity. Aromaticity is a form of extra stability that we see, and that's due to conjugation. And conjugation is additional stability due to alternating single and double bonds. So in this molecule down here, we have a double bond, a single bond, a double bond, a single bond. And basically what we can think about for conjugation is it's a highway for electrons. The electrons can race back and forth on this molecule, and that stabilizes the whole thing just because the electrons have more places to go. And so then for aromaticity again is a special form of conjugation, and it deals specifically with rings. And so these rings on my molecule are what are giving this molecule this aromaticity. And so another thing that's really important to know is that aromaticity and conjugation stabilize any kind of molecule, not just radicals. So they're important stabilizing factors in most of the things that chemists are trying to make. And what it does is it allows this lone electron to skate freely around the whole molecule. And in doing so, we're lowering the reactivity of the molecule because even though the electron will be spending most of its time on this central carbon, it can move to other places, which means that central carbon isn't too overreactive when we're talking about making sure that this is a stable species. And then the next feature that I was looking at was something called steric hindrance, which is just a really fancy chemist way of saying physical barriers. And so when we look at this molecule, I'm talking specifically about the chlorines when I'm talking about steric hindrance. And so in this 3D model, maybe, there we go. You can see that as we're spinning around, the green chlorines are arranged in such a way that they are kind of blocking this beige carbon in the middle, which is where that radical is going to be spending most of its time. And when we're physically barricading this radical off, it's just helpful because it can't interact and therefore react with things if it just physically can't reach them. So it's a pretty basic concept, but it's important to understand. And so you can kind of get the sense that, okay, these chlorines are kind of blocking here, but a better idea is the space-filling model. So chlorines are really big, fluffy atoms. They take up a lot of space. And in doing so, they are very specifically helpful for steric hindrance because as this molecule is spinning around, you occasionally can see that beige carbon in the middle. And because we can only barely see it, we know that these chlorines are going to do a good job of blocking where that radical is, making it less reactive. And then finally, the last feature that I was looking at was the presence of heteroatoms. So heteroatoms are anything that isn't a hydrogen or a carbon. And so in our molecule, we have chlorines and nitrogens. We just talked about the chlorines for steric hindrance. So we're focusing on the nitrogens when we're talking about heteroatoms. Heteroatoms, and specifically nitrogen, is really important for luminescence. So we're going to go back to luminescence. I know you probably thought we were done talking about it. So here we have another diagram. We've already seen one like this. So the interesting thing about luminescence is most molecules actually do luminesce. It just isn't within the visible light spectrum. So benzene, this molecule here, can absorb energy and then emit light back out. But it's too high of energy to be within the range that we see color. And so when we introduced some nitrogens into our compound, we end up lowering the LUMO such that we can have an emission of a photon that's within the visible light spectrum so that we perceive light. So the takeaway here is that heteroatoms are going to lower our HOMO-LUMO gap, and in doing so are going to allow us to have a photon that is emitted within the visible light spectrum so that we see color. So we're going to go back to our compound and kind of review what we just talked about. So the first thing is aromaticity is really important for stability of our compound. Chlorines are important for steric hindrance, which is important for, again, stability. And then finally, these nitrogens are important for the ability to luminesce. And so when we look at this compound, the next thing, my project was based off of making this compound. So when I look at this, I have to figure out how in the world am I going to make it. And so the first thing you do is you dive into the literature, and I found a compound that looks like this. And so I saw this compound and I said, okay, that seems like a good starting spot for where I want to go. The reaction for this involves these two starting reagents, a strong base, and then you mix them all together and you end up with that compound. The kinds of strong bases that are required for this reaction to run are things called pyrophoric bases, meaning that they are very sensitive to air and water, such that some of them actually light fire when they interact with air. And so not only for safety, but also just for the success of this reaction, I had to be very careful when I was dealing with it to make sure that the reaction was air and water free as much as possible. And the reason why we need these strong bases is because the strong base is going to come in, it's going to steal this hydrogen off this carbon, which then will allow that carbon to attack this carbon here, and hopefully we end up with this intermediate product. So the question is, what strong base do you use? And this was the reaction that Graham was referring to. This reaction took me about a whole summer and then like another half of the school year to figure out what was going on. So the first thing that I tried was store-bought LDA. So the literature called for this base called lithium diisopropylamine, which looks like this. And so we had a bottle in the stock room, and DMARC just handed it to me, and I ran upstairs and ran this reaction, and nothing had happened. And I was like, okay, how does that happen? Well, one of the first things that is interesting to know is that LDA is, as a commercial solution, is particularly poor quality. So a lot of chemists generally just make their own LDA because it's a pretty easy reaction. So when I didn't get any product, I wasn't too upset, and I said, okay, scratch that, we're gonna move on. So the next thing that I did was I tried butylithium. And so if I was gonna make my own LDA, here's the reaction for making LDA. And when I look at this, okay, you take diisopropylamine, you use butylithium, which is another strong base, and then you make LDA. And I thought, okay, maybe I can just skip that step and just use butylithium instead, because then it's just less work for me. But unfortunately, butylithium is a much smaller base and much more reactive than LDA. So I ended up with a lot of gunk, a lot of side product when I was running this reaction, and it wasn't easy to purify. So I said, okay, never mind, we'll just push through, and ended up making our own LDA. And so when I ran this reaction, I was finally able to get a good yield. Unfortunately, the good yield, at the end I got 31% yield, which is pretty good. But before I was able to get 31% yield, we didn't have a functioning glove box. And so I was doing all of this in a hood in the hot, humid Wisconsin air, which is full of water, which is not an easy task. And so before we had the glove box, I was only able to get about 10% yield on this reaction, doing like everything I possibly could to make it air-free. So this was certainly a challenge. So the glove box helped me a lot in this reaction, thank goodness. So then once we have this intermediate product, it seems pretty easy. All we have to do is throw another ring on there. It seems pretty basic. But unfortunately, alcohols, this OH group here, is not very good at leaving. It likes to stick around. And so I had to modify it using something called methane sulfonyl chloride, which reacts in order to make this mesyl group here on the top. And luckily, a mesyl group is much more likely to leave than an alcohol group is. And so this is just supposed to help me in that last reaction step that I have, which is to add that last ring on there. And I was able to run this at about 49% yield. And luckily, this reaction was not air or water free. I could just do this one under it. And then we get to finally the last step of the reaction process, which is to take this starting reagent again and reacting it with my intermediate product that has now been modified in order to get this precursor molecule. Oh, JK. So anyways, okay, so you start with LDA, and you take LDA, and it's going to, again, take this hydrogen off, and you're going to have this carbon. It's going to attack here, and then we end up with our precursor molecule. And as you can see, we don't have a radical here yet, because this is just the skeleton for what we're trying to make. And so this reaction has the same procedure as that first step, and unfortunately, it is even more air and water-free reactive than the first one. And so I wasn't able to get a clear yield because I'd been working on the project for about 1.5 years by the time I had run this reaction. And Graham turned to me and said, we should just try and make a radical. And I said, that's a great idea. So we pushed through, and so there's 2 ways to make a radical. There's 2 steps to make a radical. The first step is to use a strong base, which terbutoxide is a very strong base, which is going to come in here and take a hydrogen off this central carbon, and we're going to end up with this anion here on the right. And then after you make the anion, you use an oxidizing agent, like iodine, to then strip off a single electron, and you end up with this radical here. Unfortunately, we were able to make the anion, but not the radical species, and a lot of that has to do with just choosing a better oxidizing agent. A very common oxidizing agent for this radical stuff is something called silver triflate, but unfortunately, because of the nitrogens on my molecule, silver is more likely to interact with them, so we are trying to avoid using oxidizing agents that have metals in them because nitrogen is very readily available for bonding with metals. And so when we look at this, one of the biggest problems of this project is the balance between stability and reactivity. So we are designing molecules specifically for them to be very stable radicals, which means the molecules that we're working with to turn into radicals are also incredibly stable. And then we're trying to take this unusually stable molecule and then force it to become a radical, which we've already talked about. Electrons don't like to be unpaired. So we are making a more stable molecule and then trying to force it into a radical species, which is not an easy task. And that's why this project is really important. It's because if we want to make the most use out of stable luminescent radicals, we have to be able to make them. And we need to know what properties are absolutely necessary to them being stable and then also making them luminescent. Because this is not an easy task at all. And we're trying to figure out what properties are totally essential for both luminescence and stability. And then finally, so my future work on this project is to purify that the precursor molecules. So like I said, we kind of just pushed ahead and saw if we could make a radical. And so making sure that we completely purify, have a good method for that, and then also characterize that precursor molecule before we move on to the radical. as well as finding the perfect base oxidant pair. So finding an oxidizing agent is going to be really key in this project because, again, those nitrogens are not easy to work with. And then finally, when we get the radical, just spectroscopy. So characterization of it and looking at its stability as well to see if it is luminescent at all, which would be wonderful if it was. Hopefully it will be with the nitrogens. And then I have some acknowledgements. So Graham isn't here, he's teaching class right now. But Graham, obviously, I wouldn't be able to have done this project without him for the last 2 years. The entire chemistry department for their support over the last 2 years and full 4 years. And then DMART and stockroom staff. There were so many days where I just like needed a hug. And DMART was there after I ran the reaction for like the 30th time that week and it wasn't working. My research lab colleagues over the last 2 years and then the Chem Senior class, as well as the Lawrence Excellence in Science Fund and the American Chemical Society Petroleum Research Fund for funding this project in the first place. And then I have a fun picture of luminescent stuff from the lab. These aren't radical species, but they are luminescent molecules and they're pretty cool to look at. I'll take any questions. Yes, ma'am.
I have 2 questions. Can you go to when you made the negative on the carbon? Yeah, so you were talking about steric hindrance. How did the base even get in there to remove the hydrogen?
Yeah, that's a really great question. Terabutoxide is just like what people use. And we assumed that we had the anion because we had a major color change. But we didn't characterize the anion well enough to know if we for sure did. It could have been removing hydrogens from somewhere else as well. But we just kind of assumed it was, and we're excited to just try to make it radical.
Could it be possible that it could like remove a hydrogen from somewhere else, but then those electrons just come in because those rings are more stable?
Essentially,
or
yeah.
like, okay. Well, then I'll keep the last questions.
Okay.
I guess while you're just on that slide, 1, great job, by the way, it sounded great. 2, do you normally use halides to create the radical species from the anion, or is it when you have those nitrogens so you can use the metals, or?
Yeah, so it's usually because of the nitrogen, so those species, but a lot of papers that don't have any nitrogens in those compounds, they're using something like silver triflate or things of that nature. So Mick, who was also working in
Yeah.
research lab, was able to use silver triflate for that. Yeah, 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 that was nice.
Can you, like, I don't know, explain how something would go and take 1 electron, and how that would work?
So it's because it's an oxidizing agent, that's like how it works. I don't really like understand the mechanism super well, but like we're choosing reactants that are known for being able to do that. Yeah, sorry. Did you have another question?
I did. Did you want to ask one?
Nope, you asked.
Can you go to your Jablonski diagram of the triplet state? With like, there was a diagram with the electrons filled in. So like,
About this one?
yeah. Okay, so what's making the spin change in the intersystem crossing? I don't know if that's too like p-chemy, but I'm curious like what's making that quantum number change when it's when the intersystem crossing happens?
I don't know. I just know that it is losing energy in some way that is like forcing the electron to change its spin. But yeah, that's very p-chemy.
Okay.
Yeah.
That's curious.
Can you go to the first slide you pulled up for us?
For,
Just the one you started with, Nikki.
oh, this one, yeah.
Yep. So why is fluorescence close to absorption but not absorption?
Yes, okay, so I am kind of lying to all of you. So when, so when a molecule, there should actually be a line up here too. And so when a molecule absorbs energy, the electron just like jumps up to any excited state and then eventually wiggles its way back down to the lowest energy excited state, which is the singlet state. So there is like an unknown version of orbitals up here, and so the electron jumps up and then eventually wiggles its way back down to the most stable excited state, and then from there will fluoresce back down. So the amount of energy that you absorb is not ever going to be equivalent to the amount of energy that you emit back out. We just want to get as close to it as possible.
And
less emission, different type of spectroscopy. Sorry.
I mean, you're good.
So you said your work on this project, sorry, I'm that you have continuing work, but you're just about done. So is that really work for you that you think you can get done, all that stuff at the end, or is this for some bright-eyed and bushy-tailed?
I'm
new
hoping I
student
can
to
pass it
take
on. Yes. Yeah, that's the goal, is to pass it on. But
Great, let's thank the speaker again. Okay, 15-minute bathroom break, and then we will have Katie.
No, make it now. With that statement, make it wait. I was just amazing and Andy. There will be sharks with lasers.
It took me so long to realize it was every main character really
Took a lot of makeup.
It took me so long to realize that. I had no idea where the longest